This is our video review for chapters 20 through 23. So problem 1. Suppose from a large study it's known that 31.5% of college students would be willing to pay for the student newspaper. You plan on asking a random sample of 200 students if they'd be willing to pay for the paper. And this is copied from an old exam. It does not say, but specifically if they'd be willing to pay for the paper, and we're interested in the percentage. So this is a percentage problem. Let's see, so when I look at it, first thing I notice is at the beginning, suppose from a large study it's known that 31.5% of college students would be willing to pay. That doesn't sound like they're talking about a sample. That sounds like it's the population. So I think that is our population percentage. And you're going to take a sample of 200 students, so my sample size equals 200. Now, just writing that down tells me, okay, I know a population percentage. I'm going to be talking about percentages. I know my sample size. This is probably one because I already know the population percentage. I'm going to try and figure out what happens when I take a sample. Okay, so from there, now moving on. Make the box model and how many draws. Well, we're dealing with percentages, and anytime you want to talk about percentages, you have to first count how many people say yes. And so anytime you're doing a box model for counting, you can only have two things in there. You can have ones and zeros. So the ones will be for the people that say yes. The zeros will be for people that say no. Now, how many of those? We don't really know how many people are in this population. It didn't tell me. But we do know that 31.5% will say yes. And then if I do 100 minus that, so 100 minus 31.5%, should give me 68.5%. Because everything has to add up to 100%. Okay, so 31.5% of the tickets will say yes, or 1 for a yes. 68.5% will say 0 for a no. And then, if we want to do the percentage, and we're talking about box models, so if we take 200 draws and find the percentage of ones, that is like the sample percentage. Part B. When you take your sample, you will probably find blank percent of the students say yes, give or take what. So what that sounds to me like I'm talking about an expected value. I'm trying to figure out what I'm expecting. For percentages, expected value for a percent is just equal to your population percent, which in our case is 31.5%. Standard error for the percent is equal to, this is the formula I never like to write, it's equal to the population percent times 100% minus the population percent, all divided by the sample size. So this will be the square root. Make sure everything's inside the square root when you put this in your calculator. So it'll be square root of 31.5% times 100% minus 31.5%. All over my sample size of 200. Which should give me about 3.28%. Make sure that you put parentheses around everything inside the square root, and don't forget the square root. So what this tells us is if we take a sample of 200, we expect to get a sample average. Sorry, we're talking about percentages. A sample percentage of about 31.5%. Give or take 3.28% or so. Because we know we never get exactly what we expect. There's just always that chance error. So we might get a little bit more and we might get a little bit less. But it'll probably be about 31.5%, give or take 3.28%. Now, what is the chance that we picked one of these samples and we pick a sample that has more than 33% that say yes? Well, if I was to try and visualize this, all of our possible sample percentages have to follow a normal curve for a large sample size, which 200 sounds like it should be large. They should be centered at 31.5% because that's our population percentage. And we're saying, what's the chance that we pick a sample of 33% or more? Well, to do this, we don't have a table that would give us values for an average of 31.5, so we have to standardize. So z is always going to be equal to our percentage minus the expected value of our percentage over the standard error of our percentage. So the percentage that we are interested in right now is 33%. The expected value was 31.5%. If I scroll up a little bit, you can see that expected value. And the standard error is 3.28%. That should give me, for my z value, something close to 0.457. Now I pull up my normal table, and I look for a positive value of z equals about 0.45. So it looks like this one would be pretty close. But notice that's my area to the left. So the area to the left is 67.36. So let's draw a picture, because we should always draw a picture. Okay. I have a z value of 0.457, and I'm looking for the area to the right. The area to the left was the 67.36. But I wanted the area to the right, so let's do 100% minus that 67.36%, because we know that all the areas have to add up to 100. So this should give me 32.64%. So my final answer is 32.64% as my final answer. This tells me that if I pick a sample of 200, I have about a 32% chance that more than 33% of people will say yes. Now, this is absolutely 100% just coincidence that this final answer is very close to 32%. That does not mean anything. That was just pure coincidence. Number 2, Congress has passed the ban on the sale of assault weapons. Now there's a move to repeal it. Do you agree that that ban should be repealed? You ask that question to a simple random sample of 1,000 adults in Texas, which has a population of 18 million. So I'm going to write this up above. Texas has a simple random sample of 1,000 and a population of 18 million. And to a separate simple random sample of 1,000 adults in Indiana, which has a population of 5.7 million. So the question specifically is, which sample will be more accurate? Texas will be more accurate because there are more people in Texas. Indiana will be more accurate because 1,000 out of 5.7 million is a higher percentage. They would be the same because two simple random samples are the same size. So this goes back to what we learned in chapter 20, which tells us we actually don't care what the population size is when we take our samples. The only thing that really matters to us is the size of our simple random sample. That's the only thing that really matters. As long as you're taking a good sample and it's a simple random sample, it doesn't really matter how big that population was. It won't make a difference that Indiana sample was a bigger percentage of the population. That doesn't matter. What matters is the size of the simple random sample. So we'll go with that third option. Number 3. Another question posed during that survey is, what age should a person be allowed to purchase a gun? The average of the 1,000 people surveyed was, they said, 18.8 years and a standard deviation of 1.2 years. Notice this is talking about sample data. So we have a sample average of 18.8. We have a standard deviation of 1.2, and we have a sample size of 18.8. Notice we don't know anything about our population average, so this is probably one where I know the sample, and now I'm going to try and estimate the population. So find a 95% confidence interval for the average age Texans believe a person should be in order to purchase a gun. So our formula for this is going to be our sample average plus or minus z star times standard error for the average. Let's see. My sample average is 18.8 plus or minus z star. This is a 95% confidence interval, and we've memorized that for 95% it's just 2 standard errors. So So we can just do 2 without having to look it up. And now standard error. I don't know that yet, so let's go find it. Standard error for average is equal to your population standard deviation over the square root of your sample size. Now, we don't actually know the population standard deviation right here, I don't think. I think it just says standard deviation. It might be the sample, it might be our population, but that is the best that we know, so we'll just use it. 1.2 over square root of my sample size of 1,000. Oh, I have a sample size is 18.8 here. I'm sorry. 1,000. Okay, so 1.2 over square root of 1,000 should give me 0.04. So my standard error for the average is 0.04. So this is going to be 18.8 plus or minus 2 times 0.04 is 0.008. Now, you might find on the exam that the person who writes it leaves it like this. So instead of simplifying, they just leave it like this. They might even leave it like this. That's okay. Don't worry about it. That's just what they like to do for some reason, and I'm not the one that writes it. So they might just leave it as 18.8 plus or minus 0.08 years. If I put it into my calculator, I get 18.72 to 18.88 years. Now, to interpret it, now remember your interpretation is always exactly the same here. It's going to be we are 95% confident that now you either have to say population average or the average of all. So the population average is between 18.72 and 18.88 years. On the exam, there will be multiple choice questions probably on the interpretations. Write down your interpretation first and then see which one matches. Because there are only 2 correct things that you can write about confidence intervals. Do not write anything else. Anything else that does not look like this is going to be wrong, no matter how logical it might sound at the moment. So the first one is to interpret it, which we just did. The next thing is, what does the 95% confidence level mean? Well, it means something like, if we took many samples and found confidence intervals for each, then about 95% of the confidence intervals would contain the true population average, sometimes called the population parameter. That's the general term for whether you're talking about average or percentage or sum or whatever it might be. Okay. The person that likes to write this exam takes that and says, well, that means that 95% of the time the confidence interval we construct will contain the population parameter or the population average. So I like to write the first way. She likes to write the second way. They both mean the same thing. So again, these are the only 2 ways you can do it. So when you get to multiple choice, do not look at the answers. Please write down your 2 possible choices, then pick out what matches from her answers. Anything else has to be wrong. Next one. Let's see, in multiple choice, circle all the requirements for the 95% confidence interval in this question to be accurately calculated. Well, so what do you need for a confidence interval? It has to be a simple random sample, and then your data has to be either normal, which we don't normally say, or a large sample size. In this class, we really just focus on the large sample size and a simple random sample. Okay, so let's go through. Histogram of the actual sample data looks approximately normal. Simple random sample, large sample size, or histogram of the population must look approximately normal. Well, in our case, we had a large sample size. So we had a large sample size. We had a simple random sample. Because we have that large sample size, we don't really care if it's normal or not because we have that large sample size. So we are good. And finally, what was the margin of error? Remember, the margin of error is always that part that you add or subtract. So in this case, it's 0.08 years. Because it's, again, the part that you add and subtract is called your margin of error. Next, scores for the ACT exam in a previous year follow the normal curve and show an average, so that's important, show an average of 18 and a standard deviation of 6. Now when I read that, I hasn't talked about a sample yet. That's probably all my population stuff. So I'm going to write down, it tells me it's normal. It tells me that my population average equals 18 and my population standard deviation equals 6. Now, suppose we take a random sample of 100 scores. So we'll use a sample size of 100. So this is one where we know our population information and we're trying to figure out what would happen if we take a sample. So what is the chance that the sample average is a score of 17 or less? Now when you see a chance for sums, percentages, averages, we have to use the normal curve. To use the normal curve, you have to standardize. So you're going to z equals your average minus the expected value for your average over the standard error for your average. Now, once you write that down, you realize, oh wait, we haven't found the expected value and standard error yet. So expected value is just equal to your population average, which is 18. And standard error for average is equal to your population standard deviation over square root of the sample size, which is going to be 6 over square root of 100, which should give me 0.6. Okay, now let's plug that in. So my average that I'm interested in is 17. I expected to get 18. And my standard error is 0.6. So that gives me negative 1.66. That tells me I was 1.66 standard errors away from the average. That's not too bad. We expect to be kind of 1 or 2 standard errors away. Now if I was to draw this, z equals negative 1.66, I'm looking for the area to the left because it said 17 or less. So I go back to that normal table, I'm looking for negative 1.66, which is somewhere about here, so it looks like I'm about 4.95%. Now again, the person that wrote the exam used the calculator, she got 4.7%. So just look for your closest value. Don't worry about it, it's going to be slightly different. Would you be able to find the chance in the previous problem if you were told that the histogram for the individual ICT scores did not follow the normal curve? So let's go back up and look. We need to have either a normal curve or a large sample size. We have 100, that counts as a large sample size. So I would say, doesn't matter. We have a large sample size. Now let's try and figure out what matches up. Let's see, she says no because the histogram for the ACT scores must follow the normal curve. Let's see, no, we just said it doesn't matter. Let's see, no, because if the histogram for the individual ICT scores isn't normal, then the histogram of the sample of 100 scores is also not normal. So that's actually saying if your population data isn't normal, then your sample data won't be normal. That is actually true. Your sample data usually looks like your population data, but in this case, again, it didn't actually matter because we have a large sample size. So our answer is supposed to be yes. Let's see, yes, because the sample is large and random, so the probability histogram follows the normal curve. Okay, so that's saying because our sample was large enough, then when we look at the average, all the possible averages, they will follow the normal curve. So that is her way of saying that, so yes. And yes, because the probability histogram does not need to be approximately normal. Well, we know that the probability histogram of averages always will be normal for a large sample size, so that doesn't really make sense either. So let's just go with that third one. Okay, and the reason why is, let's write down here, if we have a large sample size, then the probability histogram of all the possible averages, which also works for percentages or sums as well, will follow the normal curve. Okay, and that happens all the time, and it doesn't matter what the population looked like. So no matter what, if you have a large sample size, then the probability histogram of all your possible averages or percentages or sums will follow the normal curve. Doesn't matter what your population looked like. So as long as you have a large sample size, you can do all these things with the normal curve. And see, if you took a random sample of 100 scores, what would you expect the sample average to be, give or take? That's just asking for the expected value of your average, which we did up above is 18, and give or take the standard error, which is 0.6. So we would expect to get a sample average of about 18, give or take 0.6. Number 5, the histogram, which shows all the possible averages for the draws from a box and their probabilities. That's what we just talked about up above, that probability histogram. So I'm just going to look through. So whenever we look at all the possible averages, that's just the probability histogram. So that has to be E. Number 6, the Indianapolis Star conducts a poll. Let's see, to see if they approve of the governor. They ask 1,000 randomly chosen adults. When the Star publishes the results, the article says that the governor's approval percentage among the adults is 42.78 plus or minus 3.12% with 95% confidence. This means that, okay, stop right there. This is one that's going to be talking about your interpretations. So let's go up here and write our 2 possible interpretations. Anything else has to be wrong. So it would be, we are 95% confident that the true percentage for all Indiana adults is, let's see, I'm not quite sure how to write it, is between somehow 42.78% plus or minus 3.12%. Okay, that's the actual interpretation. What does the 95% confident mean? That means that of all the samples we could have picked, and then we find confidence intervals for them, each one gives us a different confidence interval, and 95% of those confidence intervals would actually contain our true population percentage. Or, to phrase it in a shorter sentence, 95% of the time, the confidence interval we find will contain the true population percentage. Now that you have that written down, find what matches it. If the poll were repeated many, many times, and it has the same sample size, that's implied in what we did up above, the percentage of Indiana adults in the samples who approve of the governor would be between 39.6 and 45.7, 95% of the time. So it's saying your sample percentage will be in that interval if you do it lots of times. That is complete bogus. Okay, we never should be talking about the sample percentages. Let's see, 95% of the time, the confidence interval constructed will contain the percentage of Indiana adults who approve of the governor. That's what I wrote up above, so that works. 95% of the time, the percentage of Indiana adults who approve of the governor is between that and that. Nope, doesn't sound right. We can be 95% confident that the number of people in the sample who said they approve of the governor is between 396 and 458. Nope, doesn't match. And there's a 95% chance that the percentage of Indiana adults, 95% chance, when you see that, you automatically know that it's going to be wrong. Next, if you took a different sample of 500 randomly chosen adults, you would expect the margin of error for a 95% confidence interval to be what compared to our original? So this 3.12% tells me that my margin of error is 3.12%. Let's see, what are they actually asking here? Here we had 1,000, here we have 500. So we're looking at changing the sample size and what will happen. I like to draw a picture on these. So for 1,000 and 500. What do we know about sample size? We know that bigger sample sizes give us better, smaller confidence intervals. So 1,000 is going to be short and 500 is going to be long. Okay. Let's see, so we were at 1,000, we're changing to 500, so we're going to be wider, and that would be a bigger margin of error. So in our case, if we were already at about 3.1%, we need to get bigger, so let's go with that second option. Let's see, suppose they'd used a 90% confidence interval instead of 95%. So what's going to happen? Let's look at confidence levels. If you start off small, but you want to get more confident, the only way to get more confident is to get bigger. And bigger and bigger. So as you get higher confidence levels, you have to get bigger. Let's see, so we were at 95% and we're going to 90%, so it should be getting narrower or a smaller margin of error. Let's see, so the same size, well no, that doesn't work. Larger, no, we said it should be smaller. Oh, here we go, smaller than the margin of error for 95% confidence. So again, as you do the exam, please figure out what your answer is first, then look at the multiple choices. And finally, you take a simple random sample of 300 USU students and find that 62% of them ate candy in the last week. So that's all sample stuff. So we have a sample size of 300, and we found a sample percentage of 62%. Find a 99% confidence interval for the percentage of all the USU students that ate candy last week. So confidence intervals is going to be sample percentage plus or minus z star times standard error for percentage. Well, my sample percentage is 62% plus or minus, oh, I don't know z star for 99%. So I come over here, I draw a picture, I want 99% in the middle, and let's see, 100 minus 99%, that would be 1%, but it needs to be split over two tails, so I should have 0.5% in this tail, and over here I should have 0.5%. Because I just want 0.5% in the tail. Now my normal table gives me areas to the left, so let's look up just 0.5%. So I'm looking in the middle for percentages and I'm looking for 0.5%. Looks like my closest one is probably this negative 2.6. So if this is negative 2.6, this is positive 2.6, and so I'll say z star equals 2.6. So plus or minus 2.6. Oh, I still don't have that standard error yet. So we need to go find that. That's again that really long formula we don't really like. Population percentage times 100% minus the population percentage all over the sample size. Make sure everything ends up inside the square root when you do it. Now in our case, we don't know the population standard deviation, but we can guess it by our sample standard deviation, which is 62%. So when I guess, I like to do little approximated signs. So 62% times 100% minus 62% all over my sample size, which is 300, which should be about 2.8%. Okay, so standard error of the percentage is 2.8%. So that's 62% plus or minus 7.28%. Again, on the exam, she'll probably just leave it like that, but let's go ahead and finish it. 62 minus 7.28 is 54.72%, and if I add it, I get 69.28%. Now let's interpret it. So we are 99% confident that the population percentage, or the percentage of all, is between 54.72% and 69.28%. And what does the 99% confidence level mean? It means of all the samples we could have chosen, each one gives us a different confidence interval, and 99% of those confidence intervals actually contain the population percentage. Or in a shorter sentence, 99% of the time, the confidence interval we find will contain the true population percentage, often also referred to in the more general term as the population parameter. And what was your margin of error? That's the part that you add or subtract, so it looks like we add and subtracted 7.28%. 7.28%.